In this tutorial we're just going to go on about atomic structure and isotopes. So if I just drag this in here and we put in, say, a proton, I'll put a proton in the centre there. So this is typically like the Bohr or the Rutherford model of an atom. So in the centre there we've got proton, draw a line there, that's a proton, and that's an electron, and this is the Bohr model. Sometimes it's called the Rutherford Bohr model of the atom, and it's a bit like planets going around the sun. So if you look at the other tutorials and the other topics that we've covered in this, I'm going to keep it quite basic for this tutorial because it's an introduction to isotopes. But if we can consider it for now that this electron's flying around this nucleus. And now the charge on the proton is +1 charge. And that's a positive charge. And I'll just write positive in shorthand like that. So that means positive. And the electron has got a charge of -1, and that's negative. So the charges cancel each other out, and this is overall for hydrogen, because that's the hydrogen atom. So for hydrogen, it's neutral. It's got no charge. Now, if an atom lost an electron, it becomes positively charged. So even though this electron is about 2,000 times smaller, it's actually that times smaller, and this number might be a bit more accurate these days, but this is basically a rough guide to how small it is. It's very tiny, and it's so, if you remember the other tutorials as well, it's actually a long way away from the nucleus. So that all the mass is really concentrated in the centre of the atom and called the nucleus. So this will be this area here will be the nucleus, and that's a nucleus there, like so. That's the I'll just point to that, and I'm going to clear this up in a second. It's getting a bit messy now. But that's the hydrogen atom. Now, during the Big Bang, it's thought that majority of the particles that were formed were protons, and we also got some neutrons, and we got an electron, but we didn't know that until James Chadwick discovered the neutron. And the reason he came across the neutron was because the mass of the atoms just wasn't quite right. So I'm just going to get rid of these for now. These aren't playing much role in this. So James Chadwick discovered, and I'll put his picture up as well. I won't put it here. I'll put it up to the side of the video. James Chadwick, and it was actually mentioned by others as well. Actually discovered it, but it was suggested by others. People like Rutherford knew that the mass of the atoms wasn't quite right, and that's because we have another particle present called a neutron. Now if I just get that on there and actually make it a little bit bigger, because it should be a tiny bit bigger. Okay, so that's a neutron. Now that doesn't have any formal charge. It's a neutron. 0 charge. Okay. But its mass, so mass is very, very similar to the proton. It's actually just a bit more than the proton. Now in those days, they actually thought electrons were being captured inside the nucleus and were forming a neutral species within the nucleus itself. They didn't realise it actually was a particle all by itself. But I've tend to have grown up with the notion that an electron and a proton mixed together becomes a neutron, because if you think about the slight increase in mass and things like that. So that's the way I think about a neutron, what a neutron is. It's just these two stuck together somehow. But that's not necessarily true. So for all intents and purposes for this tutorial, the best thing to think about is that we have 3 particles. So that's 3 particles that make up the atom. Okay. The atom. Now I do apologise for my spelling, but the pen doesn't help. There are 3 particles in an atom, and that they are the proton. I'll draw this in. I'll just circle this a different colour. So the proton, the neutron, and the electron. Okay, they're the 3 particles that make up an atom. Apart from hydrogen, which I mentioned earlier, hydrogen atom just has a proton and an electron. It doesn't have a neutron. It's the only element that doesn't have a neutron present. However, when we talk about isotopes, so I'll just get rid of these here, give myself some more room. Oops. When we talk about isotopes, we actually mean it is a different form of the element. The element is defined by the number of protons that are present. You can have an element, say gold, and you lose an electron, it will become a charged species, an ion, but that will be still referred to as gold, and that's because it's the protons that define what the element is called. Now an isotope, I'll just write this, an isotope is just a different form. It just means it's got an extra neutron, or maybe one less, or maybe a few less. So basically an isotope is just, and I'll put the definition up on the side of the tutorial so you can actually read it, because it's very important, and if I write it, it might not be that easy to see. But an isotope is basically an atom or an element which has a different number of neutrons, and that different number of neutrons give rise to a different mass of the element. And examples of this would be carbon-12, which has got, it's cold carbon because it's got 6 protons, and carbon-13. Okay, so basically it's this number that's changing. It's the mass number, the atomic mass number that's changing. That means, this means how many protons it's got, the atomic number, but the mass number actually tells you how many neutrons are present, because that is the total mass, so that's the protons and the neutrons. So as you can see in carbon-13, it's actually got 7 neutrons. Now in everyday life that doesn't really make much difference, but when you come to observe the atoms in more detail using some spectroscopic techniques, particularly nuclear magnetic resonance, which just looks at the nucleus, you can definitely tell differences, because other properties, which are called spin, which I won't go into now, are different for these different isotopic elements. So it is very important, and also it's very important for radioactive compounds as well, because you'll see different radioactive decays based on the number of neutrons that are present. So there are more elements, if you will. There are 80 stable elements, and out of those stable elements, i.e. the ones that aren't radioactive, out of those stable elements, there are actually a lot more isotopic forms of those stable elements. And I'll put a few of those details up as well, and try and put a table up so you can see all the different forms of the common ones, like carbon-13 and things like that. And carbon-13 actually occurs naturally, and all these isotopes do occur naturally as well. And you'll probably come across these as well when you come to look at the mass when you're working out how many moles of something you need to use when you're doing a chemical reaction or something like that. And you'll notice that they've got strange mass numbers, and like 35.7 or something like that. And that's basically because all you're doing is you're adding a known ratio of one isotope to the other, which exists in different percentages. Say, just for this tutorial, say this is 1% or something like that, and this is 99%. Okay, that's not the exact figure, but it'll give you a rough guide. Now, if this has got slightly heavier mass, this has got an atomic mass unit of 13, and this has got an atomic mass unit of 12, then obviously the contribution that this makes isn't going to be 1 to the total weight. It's going to be slightly more than that because it's got a little bit more mass. So that actually gives you slightly different numbers. But I won't go into that now, but we'll cover that in another topic when you're working out the mass of your compounds. So basically, an isotope is just an element with varying numbers of neutrons, and the standard number of neutrons is usually taken to be the one that is the most naturally abundant. So in this case it will be carbon-12 is the natural one, and this will be called the isotope of it. But really they're both isotopes of each other. And that is isotopes.